All right. Okay. Well, good afternoon, everyone. How are you guys doing? Doing all right? I don't see many people here today. I don't know what's going on. I know. What? It's too cold. Yeah, bro. It's too cold and too rainy and wet. So people prefer to stay at home. Maybe. And that's kind of an early arrival of the. Well, I don't think it's an arrival of the winter, but it's gonna get warmer very soon. All right, guys, so I guess you're done with project number 5. There was one point that I wanted to discuss a little bit further. I sent an email about how to solve this problem, but there was a minor mistake in the equation I sent you. So basically, what you had to do is to find the equivalent of a diffusivity parameter. So can you see that if you look at that, that's a diffusivity equation, variation of pressure with time with variation of pressure with space, and this is your parameter that it will correspond to a sort of a diffusivity parameter. So let me rewrite that. So you could think of this as the diffusivity parameter and just solving for P. So from here, if you want to solve any type of diffusivity equation, you can calculate what is known as a characteristic time, which is going to be proportional to the characteristic length squared divided the diffusivity parameter. And this is going to tell you how much time, more or less, is going to take for that pore pressure to change according to, in this case, will be known as the drainage length. And that drainage length, we're going to go through some examples today. It's the characteristic length of the problem. So for example, if you're dealing with a rock sample of the size of 2 inches long, then the characteristic size, if you have 2 end caps on the 2 sides, will be 1 inch, will be half of that. Because that's the time it would take for, if you have a sleeve over here and you have end caps connected to pipes and to pumps, that will be the necessary time it takes a molecule of water to get out of the system. So this one will be L. Now this is not the same as the length of the sample. So in this case, your characteristic length was 1 inch, right? And the only thing that you have to calculate here was the diffusivity parameter. And in this case, the diffusivity parameter is K, where K, in order to make this clear, I'm going to add the H from hydraulic. So it's not the same K as the K from stiffness times M divided by viscosity, and KH divided viscosity, I can calculate that M, and that M, as we know from our equations, that's something that we derived somewhere over here. That was M, right? And that M, if I replace the value of 1 over N, is that. And if I do a little bit more of math, I can calculate this as, so this is going to be alpha minus porosity divided Ks plus porosity divided Kf. And this is what I missed in my email. I missed that. Okay, sorry about that. So it's the inverse of that. you you can further modify this equation. Sometimes we do not measure Ks. Ks is something that we don't really, it's not a direct quantity. It's more like an indirect quantity that characterizes the porous medium. So instead of Ks, we can work with K, and that's going to be, if I replace Ks from the definition of Ks, this is going to be 1 minus alpha, alpha minus porosity plus porosity Kf minus 1. So that's going to be your diffusivity parameter. So that was a missing piece of information to solve this problem. And after you calculate that value, then you can calculate what is your characteristic time, which is going to give you some number in seconds. My question was if when you increased, say, confining pressure with time, if this delta T was much bigger or much smaller than the characteristic time. Do you remember what was the characteristic time that you calculated from the homework?
Really small. I didn't do that. So
It's okay. If it's okay, you didn't do that, okay? But try to complete now that you know how to do it. Try to complete the project.
I know it's like a 1 second.
1 second, and I saw calculations from other people getting like also like something less than 1 second, but it's very likely it's very small. And do you remember what was the loading that it took in this actual experiment?
It's like 150 seconds.
Yeah, like about 250.
250? Okay. So let's say that would be, let's say, 5 minutes, okay, just to make it. So 5 minutes. It took 5 minutes to do these loadings. But it just takes less than 1 second for that rock to, if you load it, to release that pore pressure. So this was very like an undrained loading. If you were to do this loading in a hundredth of a second, then probably you may go into undrained loading with the same sample. Or if you were, if you were to change the viscosity of the fluid, if you were to put oil in there, you could go also into undrained loading. Let's say that you saturate your rock with glycerin or with honey. With the same loading time, you could also go close to undrained loading. There is something funny actually when you do undrained loading of samples and you follow this same procedure. We have done this in the lab, also looking at trying to measure BO coefficient of very tight rocks in which your permeability is very small. And these cycles, they start to look like that. They are not lines anymore, but they are like curves because it's a time-dependent process. It doesn't go through perfect lines, but it's just a pressure that changes slowly, and that manifests readily in the volumetric strain. Yeah, Michael?
So are you saying that the loading that we were given was drained, or I think you said?
Yes, this experiment was drained. This one was with this.
I thought you said it was undrained, and then you were saying other things were undrained.
No, yeah, this one that I gave you was drained, but we have done other experiments in the laboratory that I didn't give you the experiment that it looks like this, and that's because it's partially undrained. And if you wanted to solve actually this problem, you have to solve that equation, and you will get an answer like this one. Yes.
If we compare the time period to the characteristic time, should you compare the entire loading or every step?
Every step, I would say, because each of those it's one loading.
Like every time you increase the pressure,
Every time you change it, yes.
So that was 1 second. 1 second increments.
No,
No,
the full
no.
loading.
Yeah, the data is recorded every 1 second, but let me, where is that? So the data was recorded here every 1 second, but the process itself took about 5 minutes. So this one probably was 1 second. It doesn't matter what that value is. But the process itself, to go from here to there, took 5 minutes.
But if you're increasing the pressure every 1 second,
No, we're increasing the pressure continuously.
right?
And but to go from here to over there, it takes about 5 minutes. If you were to go from here to there,
But my point is,
Yeah.
say right now you're recording the pressure drop. You're recording the pressure change at every 1 second. Now, if your characteristic time is about 2 seconds, you don't have enough time between every step for the pressure to equilibrate. That would be unlike that would be like
the numbers that you calculated are kind of approximate, okay? That solution, this characteristic time too, it's kind of an approximate time for the pressure to go, for that change to decrease about 2/3 of delta P.
Yes.
That will give you the characteristic time. So it's kind of an approximate number too. If you were to be undrained, your change of pressure should be much shorter than this characteristic time. You have a question, Robert?
Well, if I understand the question correctly, I
Yeah.
think what's being asked is, we're comparing the characteristic time in this case to like the entire load cycle.
Yes.
If we look at just a subset of the load cycle, let's say a second of the load cycle,
Yeah.
there's still a substantial pressure change just in that segment of the load cycle.
Mm-hmm.
So why does that say, why are we not comparing the characteristic time to say just that segment of the load cycle where we already have a significant pressure change? Does that make sense?
I see what you mean. So I don't know. I don't have an easy answer for that, but to me the process where we are comparing, where we're causing this finite amount of strain, is to go from here to there, and although if you look at some of these lines, you also may see that they have a small curvature, similar to the one that I was showing here before. So probably there might be a little bit of undrained loading, but not too much. Let's take the example that now we do this in 1 year, okay? We're also adding a strain, a very small strain, in 1 second, 2 seconds, 3 seconds, but very clear that's going to be undrained, right? So probably the answer here would come on comparing what is the change of volumetric strain that we're actually doing per unit of time to the pressure that we would expect, the pressure change that we would expect.
So is there like an interval of delta P for which there's an interval of delta P for which the characteristic time would be valid? And in this case, let's say that the full load cycle delta P
Yeah.
is smaller than whatever that delta P would be. Is that one way of looking at it?
I think in order to make it rigorous, what we have to do is actually to solve this equation, which is time dependent. Probably there that we will see, according to the velocity of loading, we either will see pore pressure building up or not. So, but that will require a solution of that equation. But just in general terms, I will go by comparing the entire cycle length to the characteristic time. That characteristic time is always going to be the same.
It's essentially an assumption in a way.
I would say it's an assumption. I would say it's just a short way of comparing the time for drainage with the time of loading. But we could add here a speed of loading, and if you were to solve that equation, you should be able to see if you have undrained loading or not. Okay? All right. Okay, guys. We need to finish today with poroelasticity. Okay? So let's talk about some examples of poroelasticity and some examples actually of undrained loading. If coming back to the problem of comparing characteristic times, if you were to drain this reservoir in 30 years, probably that will be a drained loading. But if you were to decrease the pressure very quickly and drain this reservoir in a few days, probably that will be an undrained loading. We had a seminar here yesterday. It was very interesting about the guy trying to measure stresses at depth and near subduction zones. Did any of you guys go to the seminar? So you remember the guy was talking about putting a wellbore in order to measure undrained loading, to measure increases of pore pressure that were caused by changes of horizontal stress at depth. So his argument was that the diffusion time was too long for this entire system, so you could capture rapid changes of stresses in the order of a few days or a few weeks by measuring the wellbore pressure. It makes sense. I don't know how precise that could be, but that makes sense. So let's talk about some other examples of undrained loading, and we'll come back to this one later on. All right. So does anyone have an example about undrained loading? What about the guys from civil engineering? I know you have one. Liquefaction, that could be a good example. Can you tell us what liquefaction is?
It's when there's rapid dynamic loading on usually a saturated loose sand.
Yes.
Which causes a sudden buildup of a large amount of pore pressure, and so the effective stress of the sand goes to close to zero.
Yeah.
And therefore, the shear strength goes close to zero, and it starts behaving like a liquid, and things just fall into it.
And where does that increase of pressure come from?
Usually it's like earthquake loading that is trying to, the sand's trying to consolidate.
Okay.
When it's vibrated, but the water can't get out from the pore spaces fast enough because the loading is so rapid and the water can't flow out.
So earthquakes come into here, and this is a saturated sediment, usually with sands, right? And sometimes.
Sometimes gravel, but that's rare.
Yeah, that but it has to be very strong.
And usually that's when it's gravel with sand in the pore spaces.
Yeah. So, but basically, the earthquake brings together P waves and S wave, and some of those P waves, they cause volumetric strain. So, and that's what we have in our equations, right? Over here, a volumetric strain, and that change of volumetric strain with no fluid coming out or in causes an increase of pore pressure. We'll see an equation for this in a little bit. And that, if you have an increase of pore pressure and your total stress remains constant, what happens with your effective stress? Goes down, right? And actually, this is this example. It's also related to quicksands. I don't know if you guys are familiar with quicksands. but it's a similar thing. There is no effective stress in the sand. Pore pressure is high. So it's sand, which is a frictional material, would look like a fluid. Okay, what other example you can tell me about?
So then if quicksands count, do things like shear thickening fluids count?
Shear thickening fluids.
Non-Newtonian fluids that upon
No, that's a different phenomenon. It's a different phenomenon. It's a similar thing in the sense that the frictional resistance of the material changes for some other reasons than the usual reasons, but it's a different thing. Okay, sample number 2.
Rapid drawdown.
Rapid drawdown? Okay, no, but I want to go to the civil engineering example before going to that. Are you guys familiar with the Leaning Tower of Pisa? Did some of you visit Florence there and saw the Leaning Tower of Pisa? No? So the problem, it's a problem of undrained loading of sediments, clay sediments that were saturated with water. And after you put the load, you load everything, you increase the total stress, but slowly the water starts to come out from the pore space, and that makes the surface to settle and to decrease in porosity because you are increasing the confining, you're increasing the effective stress. So you're loading a porous medium saturated with fluid. After you load it, what you would expect in this case is that if, say, this is the pore pressure, originally it was somewhere over here. Immediately after you load it, the pore pressure increases, and after the pressure starts to dissipate and the fluid starts to drain, your pressure is going to go down and come back to the hydrostatic pore pressure. But that's going to take a long time. And what is that going to depend on? It's going to depend on the diffusivity parameter. And that diffusivity parameter, if you remember, we say it's K divided by the viscosity. And in this particular condition, we're going to assume that the strain is just in one dimension. So something that we have called one-dimensional strain. And in that case, instead of using the bulk modulus K that we have from this equation over here, because of the conditions in which we're loading it, we can use the constraint modulus M, where M is not to be confused with the BO modulus, okay? This M is E Young modulus 1 plus Poisson ratio, something like this. Poisson ratio there too. Is the constraint modulus, because of we have strain just in one direction. And what do you think if we had here a bedrock of very tight rock? What is going to be the characteristic drainage length?
The entire depth down that.
The entire depth, because a molecule of fluid will have to go from here all the way up in order to get out of the system. It cannot go down because that's an impermeable barrier. So it has to go all the way up. And so if you wanted to calculate what is the characteristic time for that, then you will have to use that L divided the diffusivity parameter. I guess we don't have a lot of time to do this, but you will see that that characteristic time increases with the square of the length. So the longer your formation, the much more it's going to take to that pore pressure to decrease with time. And also, if you have rocks and sediments with a very low permeability, that's going to readily affect what is the diffusivity parameter. And of course, viscosity too, right? But for most fluids that we have in the subsurface, viscosity doesn't change that much unless you have a gas. A very similar problem to this is the problem that we find with sedimentary basins, in which as they form, and this is water somewhere over here, here we're in Galveston, as you drop sediments and you form sediment layers, the materials in this location, they start to get buried, and they will also deform, mostly, if you don't have any tectonic strain, mostly in one direction. This problem over here is called the consolidation problem. And this one over here, which is exactly the same but in a different context, is called the disequilibrium compaction. So let me continue with the story. What's going on over here, as you get buried, as this one gets buried with time, the porosity decreases. If porosity decreases, the fluid has to come out of the pore space, but that's going to take time too. And it's going to take a time, again, proportional to that diffusivity parameter. As a result, what happens in many of these places is that as you go deeper and deeper, what you would expect to be the hydrostatic pressure, it might be true for some sections which are closer to the surface, especially, say, if you have a sandy reservoir here, and here you start to get into clay-rich sediments, you will see that the sandy part, because it has a high permeability, will be mostly a hydrostatic pore pressure. But as soon as you get into the shale part, the pore pressure is not going to be hydrostatic, but it's going to be different, and it's going to be a value which is higher than the hydrostatic pore pressure. So this is a problem in which there is still sort of undrained loading. The pore pressure is dissipating very slowly with time. And if you make some numbers considering viscosity of water, permeabilities in the order of microdarcy to nanodarcies, typical of clay sediments, you will see that for a 100 meters layer, it can take up to 100,000 years or 10,000 years for that pore pressure to dissipate. So in many sedimentary basins, especially in Gulf of Mexico, there is a lot of this. You have these variations of pore pressure in which the pore pressure is not hydrostatic, but it is higher than hydrostatic because the sediment has suffered, and it is today suffering still undrained loading, and the pressure is dissipating very slowly with time. Yes, person.
So is that just because the rate of loading through the sedimentation is relatively small over time?
Yes, exactly. Thank you for that. I was forgetting that. So this phenomenon, disequilibrium compaction, will happen, as Preston said, whenever the rate of sedimentation is bigger than the rate of pore pressure change or pore pressure diffusion. If you have that, if you add the sediments very quickly and the pore pressure cannot escape, then you will lock in that pore pressure with time. Yeah, Robert.
So would that be correct to say that it's because the rate of sedimentation is faster than the characteristic time?
Yeah, so I think you get into a good point, and there we can close our previous discussion. We compare rates to rates and times to times. Okay, so in the previous example, also in order to be fair, we should have compared rate of loading to rate of pore pressure diffusion. So if we do that, then we're comparing apples to apples. Yeah. Very good, very good. But it's exactly the same problem. And this is a very common problem in offshore basins. Actually, some people take advantage of this, and that's something that you're going to do in project number 7, I think, is to take advantage of the porosity. Let me plug here porosity with depth on this line. How would you expect porosity to behave as you go deeper and deeper? It should decrease, right? But if you have overpressure, you will see your porosity actually not to decrease at the rate that you would expect for that effective stress, but it will tend to deviate from that. So later on, we're going to take advantage of that porosity in order to calculate this pore pressure. And that's something whenever your pore pressure is higher than the hydrostatic pore pressure, is called overpressure. And there is a parameter to measure overpressure, and it's defined as the actual pore pressure divided the vertical stress. By the way, your pore pressure can never be higher than your vertical stress. Okay, we still have some theory to work on, guys.